Dus in theorie zou je mij nu moeten horen. Ja. Ja.
Ja, yes.
Je moet hem laten aanstaan nu en zet gewoon een mute aan van boven. Als je...
Hello? Maar ben ik... Hello everybody? Can you hear me in the kitchen? Yes? Hello? We're going to start in 2 minutes, so get a piece of pizza and the chairs are down here on the other side of the building. So take some drinks, take some pizza, and you can go there. We're going to start in 2 minutes. Thank you. Wel, ik zou misschien die stoel daar klaarzetten. Yes. Dan kunnen we... Dat was een close call. Hij heeft zichzelf al uitwijzen. Alright. Ja, ça va. Mensen kunnen wel iets pakken als er nog nodig is. All right, going to start. Welcome in our offices to the Tensorflow Meet-up. We have a big audience today, very happy that so many joined in. So tonight we have a couple of very exciting, interesting talks, mostly about reinforcement learning and Unity, sim to real, that kind of stuff. So I'm going to give a very, very small intro, a couple of minutes. And then Ward is going to kick off with one game he has built within Unity, and he trained an agent with ML agents. I'm going to leave that to them. Then Victor from ML6 did something similar in parallel. He's going to talk to you about his experiences. And then we have a small break, and then Stan will going to talk all about AlphaZero, which will also be very exciting. Just a very brief word about, so who knows in the pocket? Who knew in the pocket before you got here? Okay, cool. We're a digital product studio. This is our office. We're actually a bunch of about 130 people, a mix of software engineers, QA engineers, designers. And we build digital products for, Colruyt, Barco. I think this is one of the applications we're very proud of. Payconic by Bankcontact. It's me. Finally, you don't need that e-reader anymore. You can just use your smartphone. Also for Demetra, it's a device that's able to detect cancer spots, melanoma, or more Barco stuff in there. This is sales enablement. This is also built in Unity. So this is a very expensive laser projector from Stenionic. It's a Barco daughter company. And it's too heavy for the salespeople to carry around. So they can use an ER application, which they can put the projector on the table and give an explanation, give a demo about the projector. So this is stuff we built for companies like Barco. And this actually brings us to Unity. So we have a couple of very good 3D engineers, Unity engineers in the pocket. We have a handful of machine learning engineers. We're sitting together and we do things together. But first, Unity. So what do BMW, Tencent, Pokemon Go, the Jungle Book movies and the Lion King movies, they're all using Unity in their products. So Unity is a 3D environment building tool, but it's used a lot these days To deploy mobile applications to iOS, but also to deploy applications to PlayStation. So they have a lot of platforms where you can build 3D environments, you can build games, and you can deploy them to a lot of platforms. Some examples you may know is Assassin's Creed, one of these games. This is just an example of rendering capacity. You all know games and what these things are able of today. So this is what you build within Unity. But Unity themselves, they're also seeing a lot of applications within industry, within augmented reality and virtual reality. So they have a whole business unit which is trying to push in digital twins, pushing Unity within industrial applications. And that's where the machine learning and reinforcement learning components start to come in. And now I'm going to hand over the phone to Bart. He will be talking about a VR game, but he will first start off with a small introduction to Unity and ML agents, which is the machine learning component that's built within Unity and where you can start doing reinforcement learning. Wow, I'm the timekeeper today. So, Bart, go.
Can you hear me? Yeah, okay. I'm gonna have a drink first because I ate some pizza and my mouth is dry. Okay. So, in theory, I have about 10 minutes to introduce you into reinforcement learning. So I have two options. Either I'll explain everything there is to know about reinforcement learning, but then I'll have to talk really fast, or I'm just going to keep it a little bit more high level. So I chose the latter option. This is also probably helping you to not get brain fried because you're here for a while this evening. So it's a bit more a high level approach. So if I had one sentence that I could use to explain what reinforcement learning is, then I would say that it's an algorithm that is learning to make its own decisions. So this is a bit different from what most code, how most code looks like. So the most code is written like in conditional programming. So you have every possible scenario, and your code has to handle every possible scenario. If it sees something that it's not used to or it's not programmed for, then your code crashes. But this is not really scalable. For example, if you want to have like a self-driving car for Tesla, we want it to understand when a woman is crossing the road, but it also has to understand when a woman is looking left and crossing the road, when a woman is looking up and crossing the road, when a child is crossing the road. If you had to program every single condition, then it's just impossible to program. So this is why we have reinforcement learning, where we have like a sort of a smarter approach in dealing this. Okay, so what is reinforcement learning? There's a certain terminology that we use to explain everything that's happening. I'll explain it to you with Bender, one of my favorite personas. So let's say Bender is an agent and he's in a certain environment. Basically what we want an algorithm or your agent to do is behave in a certain way. And we'll do this by giving him rewards. So Bender loves beer, so we want him to go through the maze and then find the exit of the maze, and we do this by giving him a reward when he exits the maze. Okay? Already here, there's a lot of possibilities. Are you going to give him, for example, you could give him like small sips of beer when he's going through the maze, and closer he gets, the more beer he gets. You could also give him like the beer just at the very end. So there's a lot of ways where you can give him a certain reward. You can have it sparse, you can have it like very delayed, but then he can do 20 things and then one very important thing, and then he gets the reward. But how does the algorithm know which of the actions was important? So this already gives you like most of the complexity in reinforcement learning. So these delayed rewards or sparse rewards. Also, like there's an enormous, okay, so we have your agent, we want it to get a certain reward. Let's say your agent is at the beginning of the maze and then it can do all kinds of stuff. So you have your algorithm that you can say it can move forward, it can move backward, but it can also flip upside down. This is a pretty stupid thing to do because it wants to get the beer. So this is something it can do, but in the beginning the algorithm doesn't know anything, so it's just doing whatever it does. Whatever it can do at random. But it could also move forward. So this is what we call the action. So there's multiple actions that the agent can do. It can flip upside down, can move backwards, can move forwards. It's however you program it. But we also want it to know where it is in the environment. So all of you and me, we're looking at this thing, we see the environment, we're gathering information. We see that it's in a certain position in the maze, but we want the algorithm to know, the agent to know something as well. So we want it to look around and read its state, so its state space. So we want it, for example, to know that there's a wall close by on its right, that there's a wall close by below him, then there's no wall above him, so that he gathers this information. Now, when it has information of where it is and then how it's behaving, so it knows its state, then we will have to take action. And this action is when you go from your state space, you want to give a certain action. So this is an algorithm, it's called the policy network. So this policy network, it can be everything. It could be like choose a random action. It's perfectly possible. But in most cases, in reinforcement learning, this will be like your a neural network, for example. But there's all kinds of possibilities. There's like all kinds of algorithms in reinforcement learning. You have your TD learning, you have your Q learning, your DQN, your double DQN. These are all kinds of algorithms that you could use to go from a state to a certain action. Okay, but this is high level. What it's doing? It's reading where it is, and then it's going to do something. In the beginning, it's going to be completely random, but then sometimes it gets a reward, and then it's learning, okay, this is probably a good thing to do, so I'll try to remember this, and it's going to try to increase its efficiency. This is basically what reinforcement learning is. So basically, we'll have this agent that wants to predict the action that will return the highest cumulative reward in the future. So if you could also have multiple rewards, so you want it to have the highest possible reward when it ends the game. This is your end goal. Okay, most of us are actually already talking about your virtual world, where you would do reinforcement learning, but actually you can also do it, of course, in the real world as well. You could have a physical maze, you can build a physical maze, you have your robot driving around, it can take its own decisions, and it can drive around and then it could hit a wall, and then eventually it'll reach the end of your maze, and then you would give it a reward, and then it's learning. The cool thing about this in the real world is you wouldn't need an engineer to create the environment. You just make a physical maze. And you can also use real physics when your car is colliding on a wall, it's just colliding on a wall. On the other side, reinforcement learning is actually, most of its power is there when we use simulated environments, for example, in this case. The cool thing about this is that we can have multiple parallel environments. So, as I said, your agent is doing random stuff in the beginning. It's learning, it's increasing its efficiency over time. But if we have multiple environments, so in a virtual world you have many different scenarios, and it's going to learn, so it's going to random stuff, and one of them is going to do something intelligent, it'll learn from this one. If you only have one physical maze, it'll take a while before it does the most efficient thing. So this is cool in simulated environments. It's also cool to break stuff in a virtual environment. You just click refresh. And you can also increase the time scale. So in the physical world, you have your physical time. In a virtual environment, you can increase stuff. You can do everything faster, so you'll end your game faster, so you're learning faster. And you also don't need like an electronics readout. So in the real world, when a car is crashing on a wall, you need like a certain detector, electronics detector, so you already need like an electronic engineer to know when it's hitting a wall. You don't need all of this in the virtual environment. It's much more simple. Okay, so I tried to give like a sort of an overview of what is possible. Like I'm talking about these state spaces and whatever, but you need to do some real programming. And this is probably not complete and not a very correct overview, but you could say that there are a lot of libraries available. So like you have your TensorFlow agents, your OpenAI baselines, stable baselines, ML agents, etc. So these are things that try to gather where you have to plug in everything together. So you have algorithms. This is the stuff that you use to update your policy. So the choices you make, like the real algorithms that are running in the background. So these algorithms are, for example, PPO, soft actor critic, DQN, double DQN, etc. But you also need your environment. So whatever your agent is running around in, and your physics engines. So this could be, most probably they're coupled together. So you have your environment and your physics together. So you could have Atari, Miyoko, Unity, Bullet, etc. In our case, we were using ML agents, which has the PPO and the SAC algorithms. Just for free, you don't need to program them. They're just there for you to use. And of course, it's using Unity because it's programmed in Unity. Okay, so now a little bit more. So I've given you a high-level overview of what reinforcement learning is. Now let's deep dive into Unity. So first of all, I can recommend you to read the paper that was published in 2018, where it has some interesting names, and one of them is the head of the ML Agents team. So you have, he was a prior head of machine learning at Amazon, Uber, IBM. So I think he knows what he's doing. But what is also very cool is the Arthur Giuliani. He seems like a very enthusiastic tech lead. He's also active in the GitHub community. He gives a lot of talks. So he also seems to know what he's doing, but probably he's earning a lot less. Okay, so I was talking about reinforcement learning. So how does this, so the high level concept, but how does this plug into Unity? So Unity, it also has a certain way of how everything is programmed. So you have your academy, which actually orchestrates the observation and the decision-making process. So it combines everything a little bit together. So in the academy, you define how fast everything is going, like your time scale, your rendering quality. So it just gathers everything a little bit together. Then we also have the brains. And the brains are the stuff where your algorithms are plugged in. So you have, for example, a player, like a bender that's running around in a maze. This is a stupid thing. So it's just running around. It can take, it does stuff. It's colliding physically, but it's not intelligent. There's no algorithm in there. The algorithm is in what we call the player brain, the learning brain. You also have a player brain, but then you can physically move your character. So just yourself, you're using your own brain. But the reinforcement learning brain is an algorithm on its own. And these stupid objects, they are plugged into this brain. But then you can have multiple instances. For example, you could have 2 robots running in your maze. And they're both learning at the same time, and they're plugging all of this back into the brain. And this brain is where the algorithm is in. So if 2 of them are running around, it's learning twice as fast. So they're all coupled to the same algorithm. This algorithm is making them make the right decisions when it's training and becoming better and better. Your academy is also linked to your Python API because you can use the Python API to just code in like you want your parameters, how fast you're running, the technical details about reinforcement, like your batch size, your learning rate. This is within Python. You define this within Python. And this is linked to the academy. Academy propagates everything to the brains. And this is also coupled to TensorFlow. So in the background, TensorFlow is running. You can also use the handy stuff from TensorFlow, like the tensor board, to look at your metrics. But I'll show you an example later. Okay, so your brain, in the brain is where you define your state space, your action space, and your reward function. But I'll give you an example of the results, what we found for our game later on. Okay, so all of this is very nice. I'm giving you an overview, but some of you are already maybe even brain fried, like, okay, you're talking about all this stuff, but I don't actually know what I have to do this myself. So how to jump right in, just go to this link. This link will show you an example of how to set up everything. So it'll teach you how to set up the ball in Unity. So this is a Unity environment. It'll teach you how to make the ball, make the square, and then give you a whole tutorial about how a ball could learn to hit a cube. That's it. So it's a very nice example. Just take a half a day and you're set, and you have your first reinforcement learning algorithm running. It also has multiple examples, so they range. I'm not going to go into detail because it's too much. But they range in complexity. So you have, for example, a player that's has to learn to go to the big ball and can go left or right. That's what it's learning. But it can go to really complex stuff as well. So for example, this is a spider and it's learning to crawl. So this is something, so going left or right is something completely different than moving 4 joints and then trying to go forward. So this is a really complex task. This is a really easy one. And the ML Agents provides for multiple of them. So this is also very nice. Another example, for example, it looks really easy. So you have your 4 players and they're just playing soccer, but there's a lot of stuff going on in the background. So you have your adversarial learning. So you have red team versus the blue team, but both of them are like you have also an attacker and defender. Both the attackers are plugged into the same brain, so they're learning the same thing, but they're in different teams. And the same thing for the goalie. All of this stuff, it's complex, but you'll see how this goes in the example. Another example is one of the things that's also available off the bat in Unity. So you have your player driving around in an environment, and it's just learning to ride along and not crashing. There's also a lot of stuff going on here as well. For example, we see where this player is, so you can see buildings, you can see trees. All of this is not interesting for the player. So it's not interesting to go left or right for this player. So what is interesting is to know how far the walls are. So it has these raycasts, so these objects you can use in Unity. So it has these raycasts, and it's casting how far everything is. So it knows how far the wall is on its left, how far the wall is on its right, and it's using this state space to then decide to go in which direction. Okay, so I've given you an introduction to reinforcement learning, Unity, and ML agents. So what did we make? We, and with we I mean Dieter, who we call Dietz. I think he's here tonight. Yes, he is here. Amazing guy. He's an AR engineer and one of our Unity experts. And this is myself. And when we create something, we always call it a Dietz production. He's called Dietz, I'm called Wart. And this is the game that we've made. You can play it yourself at the end of the evening, so it's positioned there in the back. So if you still have time, you can play it yourself on our Oculus. So this is how the game looks like. I don't have the sound on. Okay. So we have our this is you. This is the blue palette is you yourself. You're connected to it with the Oculus. The red palette, so the red bracket is our reinforcement learned player. So this is what we trained, and it's pretty good. So you can try to beat it yourself. Good luck. Okay, how did we do all of this? So how did we create this game? When you look at 2D Pong, it's something that's pretty easy to implement in Unity. So this is pretty easy. And also, I told you that there's a lot of examples available in ML agents. And one of the examples is where you have two players playing against each other, and they're learning from an adversarial learning. So they're training themselves a little bit. And they're just trying to learn to keep the ball up as high as long as they can. And whoever is responsible for hitting the ball over or missing the ball, this one gets a negative reward, and so it's training to keep the ball up the whole time. So we had 2D Pong where we could start from, and we had this example that was very similar to our end goal. So how hard can it be to implement a 3D Pong game where rackets just play against each other via reinforcement learning? So we just say start from this and then just adopt a little bit until it works. Well, this is wrong. So reinforcement learning is not easy, and that's why if you want to remember something about the whole evening, I'll just set up some ground rules which you can follow, and it'll help you a little bit not get stuck when you're doing stuff wrong. So rule number 1, start with a simple environment. Why is this? So the environment is your Unity environment. Why do you want to start really simple? Because when you're looking at all of the stuff, you could say that there's 5 steps that you can do to do your reinforcement learning. You can create your environment, which is a big step, so you have to create all these physical objects. You define your agent state space, so you define what it can know from the environment. The action space, so you define what it can do, go up, go down, go left or right. You create your rewards function, so when does it get a positive reward, when does it get a negative reward? And fine-tune your hyperparameters. Hyperparameters is a bit more technical. I won't be going into details. These are the 5 steps that you think you can do. So this is not really correct as well, because actually it's more like this. When you have these steps, but then they're all linked together. If you're changing your state space, then you're probably going to have to change your rewards. You have to change your hyperparameters to make it work more. It's a really complex ensemble. So whenever you're changing something, you might break something. So you have to start really simple and then increase your complexity step by step. So don't try to take something that's already pretty complex and move it towards your end goal. In our example, we started from this tennis player, this tennis player game, And when it wasn't working, we were already really thinking like, okay, we're going to have to use curriculum learning. So this is a technique where you start simple and you increase your complexity. This didn't work. Then we thought maybe we should change our reward function a little bit. For example, in the beginning, we had your racket. When it hit the ball, we gave it a +1. When it missed the ball, we gave it a -1. That's as easy how we started. This didn't work. So then we were thinking maybe we should give it like a reward when the ball is going in the right direction. And we were thinking way too complex. And other examples when we're thinking like the adversarial learning, we'll exploit this a little bit more. When we were looking at like the technical TensorBoard metrics, we were trying to figure out what was going on technically. But we did make it work when we just started simple. So this is an example of how to start simple. We have this ball that's starting at the end, it's spawning in the middle, and it has a certain random direction. And then this is our agent, and we trained it to get a +1 when it hits the wall, and a -1 when it misses. When it hits the ball, and a -1 when it misses the ball. So it's very simple. This worked pretty much off the bat. It was really easy to implement this, and then we could increase our complexity. So the second thing we did was we increased the randomness. So in the beginning, you had your ball, and it had a sort of conical way of where it could go, a certain direction with some randomness. But then we increased the conical shape, so it could also hit the top wall and then bounce down, or the side walls and then bounce down. And we saw that it actually didn't train, or it wasn't perfect. So I'm not going to explain all the details here. What you could look like, you could look at this plot first. So what this says is that all the different steps that we took. So a step is a certain action it's going to take. But we saw in the previous example, so the really easy one, that after only 80,000 steps, we had a perfectly trained agent. It was constantly hitting +1. So it was always hitting the ball. While in our second attempt, where we increased the randomness a little bit, it only hit an average score of like -0.5. So it was missing the ball more than it was hitting the wall. So we solved this by just adding more parallel environments. So we first only had one environment, but there was just not enough scenarios where it could learn from it. So it needed a lot of things to try before it was learning very well. So we increased the environment. So we didn't only have one environment. We copied everything. We had 36 environments. I don't know the exact number, but there were multiple players playing at the same time and learning a lot faster. So this is how we solved the first problem. And this is, I think, an example of where you have this higher randomness and it's hitting the walls, and then it's still capable of learning. So this is a perfectly trained player in this scenario. Then we added like an extra randomness in the position of the ball. So it was always spawning in the middle, random direction, but now it's also a random position at the end of the wall. Again, we didn't have a perfectly trained brain, so the blue one is the one with the extra randomness in the position. The red one was the previous one. So again, it never got to the very extremely efficient player. So then we had to play around with the hyperparameters. Again, technically, it's a bit technical, the hyperparameters. I won't be going into details, but it's just like how you fine-tune everything in your neural network and etc. But we had to play around with this. What we did, we actually had a perfect player and it learned all of this in only like 50,000 steps. So playing with these hyperparameters is really important, but I cannot give you sort of a guide how to use these hyperparameters. You just have to play around with them. Fourth thing, then we let the ball bounce back and forth. So first it was just stopping when it hit the ball and stopping when it missed the ball, but now we just let it hit the ball back and forth, so it's learning to play against itself. This is again an increase in complexity. And then we also added random velocities because it was only trained at one velocity, but we wanted a game that increased in difficulty. So we didn't want to train it at one velocity, but at multiple velocities. So we increased the randomness in the velocities. Sixth thing that we thought of doing was add this adversarial learning. So when it's training against itself, we were thinking about this, and then I realized, no, I just have to keep it simple, because if you think a little bit, a player that's trained against itself, that is trained in for every single velocity that you want, every single direction, every single position, that is just a perfect player. You don't need to train it anymore, because it can handle every possible scenario. Okay, so this is how we developed the game. This is a bit more technical. So this is the code that you write then in C#. So you have your state space. You have, so what it knows is its own position. Its position, so it's the velocity of the ball. So it knows what is going on in its environment. We also give it like the action space. So this is the stuff it can do. So your player can just go up, down, left, or right. These are the 4 actions that we define. But you can already see that we also give it, there's also rewards popping up. So we give it a really small negative reward. And why is this? Is that we don't only give it like a +1. I'll just show you here already. So we give it a -1 when it misses the ball, give it a +1 when it hits the ball. But we don't want the player to just constantly do this. Like, this is useless, but it just doesn't look nice. So we want to detrain it from going around randomly without having to increase its chance of hitting the ball. So these random noise movements, we don't want it. So that's why we give it like very, very small negative reward, because it's doing a lot of these movements, and we give it every single frame. So that's why you want to have it like really, really small, because otherwise the rewards are just too big. The second rule is that Unity is an ML agent. It has a small but active community, but just don't always rely on the docs. So it's an active community. But for example, when I had a certain question, where I was reading this interesting article and I asked them, like, could you maybe implement this? Then you just immediately give me an answer like, just do it yourself. So they're active and they're really, really good guys, but they're a limited community. So if you want something interesting to happen, you're on your own often. Another example is like many of these discussions are suddenly killed off. We had a problem. I explained to you what we were doing wrong. We didn't understand it by then. There was one interesting person that responded. Some of you might know him. He's standing right there. But nobody else answered, and we just had a stale bot that just killed off the discussion. So often you're on your own. This is another example. I actually found a bug, and I think at some point, I communicated it back to the people from ML Agents. They just said, yeah, agreed. It's weird. We're trying to find some historical info on it. Never got an answer. So that's why I'm saying they're really cool guys, but you're on your own. Okay. Another thing that you often will see is when something's not going right and you're looking at your technical details, they'll often answer you with what buffer size you're using, what batch size you're using. So these are your hyperparameters, very technical. Then he's going to recommend you to change your hyperparameters. Then somebody else had a problem. He asked to decrease your learning rate. So this is again your hyperparameters. So when they don't know, they just tell you change your hyperparameters. Another example, did you train longer, or maybe you could use some other hyperparameters. So again, they don't know everything. It's not easy. So you have to do a lot of debugging yourself. Rule number 3, we also did some stupid stuff in Unity. So be cautious of Unity itself. It's really cool, and if you know what you're doing, then it's really powerful. But we were doing some stuff that made it not possible to have decent learning. For example, in the beginning, our game, whenever it collided against a wall, whenever our ball collided against the wall, it lost a certain portion of its velocity. So it was always going slower and slower and slower. A human would say, okay, that makes the game easier, but for a computer, this is not the case. So it wasn't really learning well, because the state space was constantly changing. It couldn't learn because everything was changing for him. We also had problems with our collisions. So we were using a setting in Unity where we had a ball that was going, it was in this position, and a frame later it was in this position. Then we have a wall here, and another frame later it was halfway through the wall, halfway it wasn't through the wall, and then Unity flips, and then it tries to explode them because they couldn't be in together because they were physical objects, and then my ball was just flying away out of the game, and I didn't know what was happening. My fault. Okay. So be cautious of this. We were also doing like a previous setting that we used for another thing that we were doing in Unity. We had our physical computations set very high on somebody else's computer. His computer could handle all the physical computations, mine didn't. So the physical computations were wrong. Another thing that we encountered is that the version of ML Agent and Unity were not synced well, so a certain version of ML Agents was not capable of handling a certain version of Unity. Everything crashed, we didn't know why. This was the reason, but they also didn't have a really good documented way of saying which version is linked to which version, so we don't have this available. They were going to work on it. Fourth rule, machines aren't human. And why do I say this? Because at the beginning, we also tried to have an agent that was not learning to move left, right, up, or down. We were trying to learn an agent that is changing its velocity. So it's either going faster to the left or decreasing its speed or increasing its speed, and the same for up and down movement. In my mind, this is almost the same thing. For a computer, this isn't. It's a completely different story. The first scenario where it's working, left, right, up, or down, is discrete, 4 possible actions. This continuous changement of velocity, this is a continuous process, and this changes your whole algorithm. You have to treat it completely differently. So the continuous scenario did really work for us. It can work, but we didn't look into it in detail. Discrete version was much easier. Also had some stuff where my agent wasn't learning, and I didn't really understand why. It wasn't learning to move up or down, and this is because Unity has settings where you can click and freeze coordinates, and I accidentally clicked on one of them, and it just physically couldn't move up or down. So always test your player bin. So you have this player bin, and you can use your keyboard to make your agent move in certain directions. Always use this, because sometimes your game is just not working the way you want it to do, and you can test this with your player brain. Also, something different that when you're trying to train a certain parameter, for example, at a certain velocity, then it doesn't necessarily mean that your agent will be working perfectly at a velocity, a little change in your velocity. When it's moving, the ball is moving a little bit faster, a little bit slower. A human is capable of understanding what it has to do to anticipate on this. For a computer, this is not always the case. So these are things that might seem intuitive for a human, but they're not for a machine. So just keep them in mind. So that's why we use this randomization for robustness. So we use random directions, random positions, random velocities, and this helps a lot in training. And fifth rule is reinforcement learning is really fun, but it's also really hard. So you'll get frustrated. So just endure. You'll get there, I hope, eventually. So you will make mistakes, you will encounter issues, you will become impatient, and you want to throw your computer outside the window because it's just taking too long for training. You'll get angry when stuff happens that you don't understand. All of this happened to me, but just keep in mind that reinforcement learning it's really hard. I mean, like the first algorithms were already there in like the 1950s, but it took a while for everything to lift off. And for example, AlphaZero, which is the third talk, it's also really powerful, but also keep in mind this is a very controlled environment. So there's not weird stuff is not going to happen. There's not like a giraffe going to run over your keyboard or your game. So it's a controlled environment. Nothing silly is going on. So reinforcement learning is hard when you're looking at stuff that you're not expecting when noise is there. Also, like these physical simulations that we use in Unity, for example, or in other engines, they're challenging. They're not perfect. They're not mimicking the real world perfectly, but these will improve, and we're just curious about the future. And saying this, we just want to tell you, like, you stay curious. This is something you might have seen from OpenAI when they show the video where they're trained with reinforcement learning, a robot that is capable of solving a Rubik's Cube. So this is really nice to see. Side note, it's not always working. So they still have a lot of scenarios when the Rubik's Cube falls off the hand, or they're also training it to with a certain Rubik's Cube algorithm, so they always move their face towards a certain direction, etc. So it's not perfectly trained and still making mistakes. But when I look at this, I get like giddy, yay! So we're getting there. It's just hard. It's just a hard game. It's hard. So that's it. If you have any questions, I think we have like 2 or 3 minutes now. Skip? Okay.
Hello, test. Test, test. Yes, down we go. Yes. No signal. All right, so thank you for coming, everyone. My name is Victor. I'm a machine learning engineer at ML6. I am obliged to say that we're hiring. So yeah, anyone who's interested, yeah, come to us during the pause or during anything else. We'll be happy to tell everything about it. So we're ML6. We're a machine learning company. That means that we have one thing missing that the other talk had, and that is a good Unity engineer. So we basically did the same thing. We built also something because ML Agents is actually really awesome. And actually, I think we broke every single one of his rules. So I'm just going to explain to you like how we stumbled upon almost the same rules and how your rule set is actually a really good guide way to get started with ML agents, because you definitely should. It's really interesting. So we did air hockey instead of Pong, which is a little bit different. We did reinforcement learning, but today I'm mainly going to talk about how we failed at it miserably, because yeah, we actually did it in the end, but I'm just going to talk about all the things that we hit our head on the way there, because those are the most interesting ones. So to give an idea of what we built, this is by Ruben. Ruben is my second colleague that actually did most of the work on this. And actually, we made this. So first of all, the puck knows nothing, and then it starts to actually hit the puck, like the Pong game. You can see that it actually learned to go to the puck. And then so in the second stage, so we did use the curriculum learning, you can see that it starts to score. There is no middle wall yet, but you can actually see something happening. And then in the final version of training, we actually got the wall in the middle, so it started to play on a real field. And then in the end, we did use self-play to actually make it even better. And now we run into some issues there as well, but I'm going to talk about those. So this is the environment that we built. We also made a hackathon on it. And so we also know about some of these problems occurring with other people, because we saw a lot of people trying the same things in the hackathon, and they all stumbled upon the same things. So it's interesting to talk about them. I'm going to take a little bit different approach, but the main idea is the same. So reinforcement learning, it's basically agents that take actions in an environment and get a reward back. It's very similar to what Ward said, and it's a good idea to think about it. So I'm going to go over each of those and tell you what can go wrong with them, or what we did wrong with them, because that's what we learned the most out of. But first of all, ML agents machine learning. So this is like the loop that you'll be doing. You'll be doing all of this. And the reinforcement learning algorithms are built in. So you have PPO and SAC that are built in. It's very interesting, actually, because you can choose what you want to focus on. If you're a Unity engineer, you can focus on the machine learning a little bit to train yourself. If you're a machine learning engineer, you can just use the pre-made stuff, or the other way around. Like, if you want to make something in TensorFlow, you can do that. You can actually plug it into a Jupyter notebook if you want. But you can also just try and figure out how things work. Now, that's what we said. What could possibly go wrong? Those are some famous last words. So that's what we started with. The first thing we did, okay, let's talk about the agent, the object that normally the player would control. So in our case, I'll call this the agent or the paddle, which is used to push the puck in a certain direction, right? These are the agents. So we went full speed forward. We did the exact thing that Ward told us not to do and built the complete environment, or tried to, because we didn't know Unity yet and things started falling through the floor. We just found out that debug options exist. We also had, for example, several problems where we trained our algorithms already, and then we figured out that the collider of the paddle was actually like squarish, because we had designed it in a different program. So then the puck wouldn't go in a direction that you would think it would go. So the model couldn't learn anything because we couldn't even play with it. So then we actually made a decent collider and did things right this time. But we were not alone. So like I said, we did a hackathon. There was a team name called All Compiler Errors Need to be Fixed, something you will run against time and time again, because you first want to do everything, and then it tells you, no, don't do it, because you have compiler errors. So we were not the only ones. A lot of these people in the hackathon had the same kind of problems where they didn't know Unity yet. First, get to know Unity. If you already know it, you can skip this step, but if you're a machine learning engineer trying something, first get to know Unity. So Arthur Giuliani, Wart already told about it. Actually, the documentation is very good to get started. So I can say that we also tried GitHub, and they're not very responsive, or at least they're responsive, but not very helpful. But the basic documentation is very good. So most of the things that you'll need to get started with, like the hyperparameter explanations and stuff like that, are actually all in the documentation. So I would definitely do it. And then we use the documentation to actually build our first very simple thing that worked, right? So we started with this, but it's actually, it gets the point done, right? It's not that much, but it learned something. And that's like the first thing. You will throw your laptop out of the window, like Wart said. We did it almost as well. But what is interesting is that the moment it learns and you see that it actually did something, you want to get back at it, and it gives you the energy to keep going. So that was really interesting. Then we have some actions. So we now have a player that can move around in an environment. The environment comes later. And now we want to define some actions, right? For the love of God, use your player brains. We didn't always do that. The player brain, like Wart said, is basically instead of giving control over to the machine, you map certain keys to what the machine would output, and then try it yourself first. Because let's take this example. What we tried, okay, we didn't know anything about Unity, so we put some things on in the Unity editor, and then it appeared that if you have a speed of 300, your pedal basically disappears the moment you press. So the whole thing gets reset and nothing happened. You can also put it very, very slow, or you can fine-tune it until it fits. So that's basically what we did with the player brain, is we try to figure out, okay, when the game is playable by us, then you go over to the training. Not sooner, because we did that and it doesn't work. So yeah, use the player brain. We also had the problem, that's something really specific, is that we didn't use the player brain, so we didn't know that the size 4 actually is size 3, size 3. So one of these was never used, and then we tried to figure out why one of our paddles always went to the right. Right? Because it couldn't go left, but we never tested that with the player brain, so please do. Don't run in the same problems that we did. Continuous and discrete is something that Wart already touched on as well. It's basically going up, down, left, or right, or the continuous left or right. Continuous, again, it's the same thing. We tried it, and it's not very good. If you can avoid it, do. Also, discrete just trains a lot faster, which is a lot more fun because the training is fun. So it affects training time. Then the environment. So the simulation as a whole, in our case, the environment was just the physics engine of Unity. It's probably going to be the same with you guys. We had trouble with the Unity position system. We actually, again, we didn't have a Unity expert. So apparently, if you have Unity and you code in C#, all your positions are global positions, but in the editor, they're all local positions. So it's kind of weird. We ended up using local position because of one main thing, and that is if you train an agent on one side and then flip it, it actually doesn't know what to do anymore because it was completely fixed on training on one side, and you basically have to take the local position and mirror all of its observations so that it actually does the correct thing when it's put on the other side. So that's something that we found that you might run into as well. And then we have the reward. Now, this is the interesting part. It's also the most anecdotal part because the coolest things happen here. So when the agent does something good or bad, you basically want to give it a reward, right? And as Wart already said, you can do this in any way, shape, or form. And it's actually the most difficult part because a bad reward can lead to pretty funny things. So in our case, we would say winning a game would be a positive reward and losing it would be a negative reward. But we had several stages, remember? So we had the touching the puck, we had scoring, and then we had scoring with the middle wall. So we had to change up the rewards over time, or at least in different stages. What I want to say beforehand, before we go a little bit more in what can go wrong with the reward, is that failing fast is good. This is actually a tip that we found that might not be very obvious, but if you make it clear to the agent that it's doing something wrong very, very soon, it's gonna learn a lot faster. And it's sometimes easy to find, right? If, for example, in the beginning, the agent knew nothing, and we put it in a walled-off environment in which it could try to touch the puck. But because it's doing random stuff, what it would end up doing is 90% of the time, it would just be stuck in the corner and never get out, or like sometimes get out, but it takes a long time. So if we just remove the walls, the player can fall off, and it's immediately game over, and you start again, and you start again, and you start again. And that's a lot faster in cycling, and so this is how it learns a lot faster. Also, mock steps is a really useful tool. Mock steps is just from ML agents, which basically says after how many time steps do you reset the game. And actually, you can figure out with the player brain how long it takes to have a decent path to your puck, and then set it a little bit larger than that. That's actually something that we saw work very well. And then design for failure is like what it did is not, in our case, what we started with, we had the puck in the middle and then just the player going at it. But what is actually a lot more useful is if you make the puck go into the direction of the goal, so that if the agent doesn't actually do anything, it will lose immediately. And then it will reset, and it will reset. And it will very quickly learn that it at least has to be in between the goal and the puck in order to not lose. And then it has some time to start actually doing good stuff. This is actually what we did then, is so you can see that the puck spawns with already quite a velocity. This is an older version of the environment, and you see that this actually works relatively well. So that was the courtesy of the fast training, or the fast failing mainly. So definitely use that. And then reward design is hard. We got to see some of them go wrong because we had the hackathon and several people were trying it at the same time. So we had several moments where things weren't going as planned. And what is easy to do as a human is just to think, I know how this challenge should be met, right? We know how to play this game. So you try to push the agent with your reward system to play the game like you would. But that's actually very bad, right? So one of the things that we saw was, for example, the hit and run, which is when we set the reward, a positive reward on scoring a goal, but no negative reward on not scoring a goal. So what the first thing that the agent learned was just to take a good while, then just shoot it all over the place and just get in a corner and wait. And then most of the time it would get in the other goal, sometimes in its own goal, but it wouldn't get a negative reward from that. So it wouldn't learn that that's bad, right? So that's the hit and run, we call it that. We have a bully as well. Anyone know what the bully could have done? No? If you put too high a reward on touching the puck versus scoring, it actually pushes the puck into the corner and just keeps bashing it so that it can keep its reward. So that's something that we saw multiple times, actually. So yeah, we call that one the bully. We also have suicide, which Wart already told you that there is the possibility to give a small negative reward for each step or for each move to get that craziness going away. We actually did that for existence reward. So we just gave it by default a negative reward for just existing so that it wouldn't take too much time to get its goal going. We put that a little bit too high, so that meant that if it figured out that the puck was too far away, it would just go off the ramp, because then it would reset, and then it would get not as much negative reward as it would otherwise have got. So it will outsmart you, and it's actually pretty funny when it happens, and you also always have to think, like, given this reward and nothing else, I would probably done the same, right? But it's pretty funny that it happens. We also had one person in the hackathon do on reward shaping. So instead of just giving discrete rewards, which is actually better in this kind of algorithm, instead of just saying, okay, when you touch the puck, you get something good. When you don't touch it, you get something bad. What he did was basically make a mathematical function that just said the closer you get to the puck, the more reward you get, which makes sense, but that's one of these cases where you try to push it too much into what you think is good. So what it ended up doing is it just went around it like a planet, because it always got closer, didn't get a negative reward for getting farther, and then getting closer again. And so it was basically farming the reward again instead of doing the thing you wanted it to do, right? So it will outsmart you if you get too smart about the rewards. Just set the reward on the only thing that you know is good, which is scoring or touching or whatever it is in your case. And then let the algorithm figure it out. And also we had one defending but not scoring, which is quite obvious. We had that with self-play, so that the moment that one of the two became better, the other one would just keep the puck on its own side because it knew that the moment the puck left its own side, it would just lose. So it was basically just keeping the ball for itself, which is pretty funny as well. So another thing I want to give with you is all of these rewards. Use the examples, right? Unity has already done this with all of the examples that Wart already showed you with all the different environments. So use the example that is closest to your use case and look at what they did. And most of the time, especially with hyperparameters, but most of the time, the reward shaping or the idea of rewards is already there. And you can just use it. You can just copy it. So to kind of end with, I don't know if I went not over time. OK. So to end with, sometimes you will feel like a parent with 4 kids. Like this one is losing its puck, like it's all over the place. This one doesn't want to get out of the corner for some reason. Like we didn't have the max step back then. I think this one actually gets the puck out of in the air. So we had to like lock it on the y-axis because like now it's all over the place. So sometimes you will just feel like, oh, what is happening? And like Wart said, your graphs are all over the place. Nothing wants to work. So sometimes you will feel like a parent with 4 kids. But sometimes it's really, really freaking cool. So these are the agents that came out of the hackathon. This was the winner of stage 1. This is a monster, right? It had to do 100 touches of a puck in as little of time as possible. It did it in, I think, 12 seconds, 11 seconds. It's crazy. Like it trained to perfection, which is awesome to see. And then we had the same guy actually get to the winner as stage 2, which had to score as many points as it could in 1 minute. We did it with the same seed, so every puck would spawn the same way. And it was actually pretty cool to see. But the coolest out of everything else, of course, was that we got to have a final between one team and another team and actually play against each other. And the players that came out of it were actually really good, right? So we had, I think, a best of 5. And they played the full 5 games. So it was definitely close, but it's cool to see that there's actually some, I think it resets a little bit too fast. Yeah, but you can see it later back there. It actually trains quite well, and it does some kind of cool stuff where it goes behind the puck and everything. So it's cool to see, and in the end, that's why you endure, because it's so fun if it works, when it works. So the main takeaways, to reiterate, it's just very fast. Get to know Unity first if you don't. We didn't. Read the documentation to get started, the hyperparameters, get a little bit of feel of what they do. Build a simple version of the game first, and with ML agents in mind, don't get a very crazy game already and then try to plug it in. It's not very easy. Use similar parameters than the examples, than the most similar example. Focus on the reward design, because when your parameters are good, it's mostly the reward design that will make it good or not good, and fail fast. A 7th is probably, if you think ML agents is wrong, it's probably you, like most of the time. That was my bad. I always did that. So yeah, again, we're hiring if you want to do more of this, and thank you for listening.
Okay, thank you very much, Victor. So, small side note, we didn't communicate on the talks beforehand. We didn't say anything, and we came to exactly the same conclusion, which was really funny. So, 10 minutes reward for you, just a beer and just some fresh oxygen in your brains. And then at 20 to after 8, we will start with a talk from Stan on Alpha Zero. Okay? We also set up the game, maybe, if you want the. So if you want to see the game, they're running in the back. Yeah, you can go and have a look at it. We gaan,
Bekende taal, ja, het is tijd zeker.
we gaan terug moeten beginnen. Ik ga de mensen bij elkaar
Het was
roepen.
interessant.
We kunnen straks nog even praten als we nog even zo blijven. Ik vind het wel een boeiende... Ik weet dat dat gebeurt, maar ik heb nooit iemand ontmoet die dat doet. Dus ik vind dat wel tof.
Die Ivo,
Ja, zo de beste nieuwe locatie voor een...
we zijn niet zo'n groot team hoor.
Nee, maar heel veel impact natuurlijk. Hè.
Ja. Maar ja, heel veel discussies ook. Ik ben er ook gebleven.
Ja. En dan ook verantwoordelijk voor bijvoorbeeld de oké of de dat soort zaken ook allemaal, of niet?
Oh, dat zijn eens.
Ja.
Dus alles van Colruyt Groep.
Ja.
Maar we hebben ze een beetje verdeeld in ons team.
Zo'n
Het is een aparte meet-up, denk ik.
Ja, een kleine meet-up is hier.
kleine meeting.
Een mini-meet-up.
We gaan beginnen. Alright? Okay. Time for the next reward. We're going to start the next talk on Alpha Zero. Can you get back to your seats, please? Thank you.
Test. Ja.
Misschien aan het einde van jouw talk ook die vragen of dat wordt ook nog een stukje als mensen.
Het is goed. Ja.
En als ik het vergeet, moet je maar zeggen.
Ja, ik zal...
Ja. Okay, so hello everyone. Since the last presentation, we are still hiring at ML6, so feel free to send me an email. We're actually hiring ML engineers, but also data engineers, front-end developers, software engineers, business developers as well. So there's a lot of opportunity, and feel free to send us an email. So this talk, what will it be about? About Alpha Zero algorithm, and specifically about the chess implementation, because the most known example is the Go implementation. And maybe just to know, give a raise of hands who, which people already have read the paper of the Go implementation. Okay, not that many people. And who has heard about it, Alpha Zero? Okay, that's better. So this is a small overview. The first few things will be like kind of an introduction, and then we'll go really deep, and I will explain you the architecture, how Monte Carlo tree search works, how we train a network. So it will be a bit different from the other talks. And I will try to learn you something. And what's also really important, that everybody can raise their hand during my talk, and feel free to ask questions anytime. I'll be happy to answer them. And at the end, I'll give you some insights about the problems I ran into and what the next steps will be of what I implemented. Because actually, I implemented this algorithm in only 4 days. It was during the Christmas projects at ML6. And what are the Christmas projects? It's during Christmas and New Year's time. We as ML6, all the engineers, we come up with ideas, we submit them, and then everybody can vote on the best ideas. And the ideas with the most votes, we try to implement. So, for example, this is an arcade game. This is a magic mirror which recognizes your face, and then, for example, can give you your train schedule. This is a simulation of a flying drone. These are ping pong analytics. So we have a ping pong table at ML6, and we try to detect a ball to see who scores the point. We can then replay points and everything else. And this is then my chess implementation. So why do I actually want to implement this? It's not only because it's fun, but actually AlphaZero is a very general algorithm. It can do a lot of things. You can actually just think of it as an algorithm that can search a search space. And for example, they have been using it to fold proteins. AlphaZero was used to create AlphaFold, and this is actually an algorithm that was published yesterday evening. And you can already find the code, the paper, and a podcast about it online by DeepMind. And what is really nice about this algorithm is that they just take the sequence of the DNA and they read it, and then because the sequence it's only like 1D, you just read stuff. It's very hard to know how the protein will look like in 3D. So this is a very known problem to biologists. And what they did with their algorithm, and currently they are best at it at the world, is trying to predict how the protein will look like. And that gives biologists insight into how the proteins will look, and possibly it gives a chance to diagnose Alzheimer or Parkinson's. So the algorithm has multiple usages. That's what I'm trying to say. So also AlphaZero is not the first version of the algorithm. There were previous versions. AlphaGo is the first one. And this is actually the algorithm that beat the world champion at Go, which is one of the most complex board games that is known to humanity. Then they incremented on that and they went to AlphaGo 0. And as you can see, this is AlphaGo Lee, so the one that beat the world champion. And then AlphaGo 0 was a lot better. And then they actually reiterated upon it. And as you can see, the increase in how well it performs is not that big, but the biggest change is that they also implemented it for other games. So they did it for chess and for shogi, which is the Chinese variant of chess, actually. So I also want to give some credit because, of course, in 4 days you cannot fully implement it all by yourself. What I did is, there is a Python library which has the chess rules in it, which is really handy because then I can just say, okay, this is the chessboard, this action I'm going to take, what are the possible, so this is a chessboard, what are the possible actions I can take from this point? Because chess is kind of a complicated game and it has a lot of rules and it would take a long time already to implement this. So I just used that. Then there was already a really boiled down simple version of AlphaZero online, which was implemented for really, really simple games. For example, for 4 in a row. I don't know if it's called that in English, but so it's really simple for a really small state space, and the neural network was way smaller. They didn't use all the fancy stuff DeepMind implemented. So what I did actually is I looked at the paper and implemented everything else that wasn't there. And it was actually quite a lot. And then I also have an API and an interface. This is LightChess. And this is a platform where you can play chess upon. You can send API requests with your moves you want to make, your chess moves. And then they are executed in real time in an interface. So what you can do then is play against your own bot. And what's really nice in LightChess is that there are even bot tournaments. So you can play with your chess bots against each other. It's a nerd plays. So the AlphaZero network, let's go in deep and let's talk about some machine learning. Okay, let's go. So what we see on the left side is how one board is represented in alpha 0. And it's actually a lot of planes, 118 to be exact. And then there's a lot of layers, a convolutional layer. I think most of you have heard about it. Then it goes through 19 residual layers. And then you get new planes with other features in it. And then you have a policy head and a value head. So that's a general overview. And now I will first talk about how the input is encoded, what comes out of the network, and then afterwards I will explain each of the parts which is in the network separately. So the board representation. These upper ones, which are black, white, and gray, these are actually just the last 8 boards of the game. And why do you need to have like 8 boards? It's kind of weird. Why can't you just have the last one? It's because in chess, there's a rule, and it's called threefold repetition. If you go into the same board 3 times, then it's a draw. So, as of course, the algorithm wants to avoid that, mostly because usually it's capable of winning. We want to have that information in our input representation so that it can act upon that. And then we have some additional state information as well, which I will go into later. So we saw the last 8 boards. Now I will show you what one board looks like. So the white ones, the white planes are the one-hot encoded features of the white pieces on the board. The black planes are the one-hot encoded black pieces. And then the number of times the board already occurred earlier in the game. That's actually what I told you about the threefold repetition, which is also in here. So how do these planes actually look like? You can look at here. This is the starting chessboard, and then you can see it just encodes it 1 plane for each piece. So the white horses, 1, 1, and the rest of the board is 0. The white rooks, 1, 1, and the rest of the board is 0. And so, the rest you can figure out yourself. Then there's also the black pieces, which is actually the same. And then you have this number of times the board was already occurred. And that's actually a binary representation. And 1 plane will always be the same number. So, for example, here, this board wasn't seen before because it's the first board. If this board would reoccur once, it would have this plane as a full 0 and this plane as a full 1. If it would have occurred twice, 1, 0, and 3 times 1, 1. And then it's a draw. And then the additional features. So that's the color which is moving, so black or white. The total move count, this increments every move. The castling rise, which is a chess term. It's when you swap the king and the rook. It's something really technical about chess for both black and white. And then no progress move count, because this is another rule in chess. If you have 50 moves where the chessboard doesn't evolve, so that means a pawn hasn't moved or a piece hasn't been captured, then it's also a draw. So let's see. Okay, then so we had the input. Those were the input features. Now let's go to the output. And the output is represented by 2 parts. You have the value and the policy. So this is the value head of the network, and it just gives a score to the board. On the left side, you can see that white is losing, so lost actually. So it will get a score of approximately -1. In the middle, it's not decided yet, so that will be equal. And on the right side, white has 1, so it gets a 1 as value. Oh, let's go back. Okay, So this is the policy network, and this is a little bit more complex. And this is actually, to me, because is a reason why the chess implementation of AlphaZero is nicer than the Go representation, because it's very hard to have a consistent action space of a chessboard, because you need to take into account how far your piece is going, but also from where it comes. And this always needs to be the same because you can't change a neural network. And so what will it be? It's also planes, like the input state. It's actually 73 planes, which have 8 by 8 dimensions. And then all of these planes, all of these cells will actually have a number from 0 to 1, which is the probability that the algorithm is going to play this move. Yeah. Okay, and so what's also important is how are we actually going to do this? How are we going to encode the action space? And the most important part is that each 8 by 8 plane represents from where the piece is moving. So later this will become more clear because I have some examples, because I know it's hard to comprehend sometimes with just text. So in each of these 8 by 8 planes you have the starting position, and then what the plane defines is where it goes to. So plane 1 says, for example, go 1 step to the north, in all the possible positions that a piece can be. It can also say go 1 step to northeast. And these are called the queen moves. So you can go forward, you can go backward, left, right, and also in the diagonal directions. So there are 8 directions, and you can go 7 squares far, because a chessboard has only 8 squares, and you start at 1, so you have 7 left. So then you have 56 planes. You have 8 knight moves, because a knight, it can move in an L shape, and you can go in 8 directions. And then you have 9 under promotions, which is kind of a special case. Usually when your pawn gets to the end of the opponent's side, you promote to a queen. But sometimes in chess you don't want to do that. You want to choose another piece, and this is actually one of those are all the possibilities of under promotion. So you can go to if you take a piece on the top left, then you actually go northwest. If you go straight on to the other side, then it's north, and then northeast. And then you can swap your pawn for a rook, bishop, or knight. So if you multiply these, you get 9 planes. Okay, so maybe it's a little bit hard. So now I can show you the way with some examples. So the queen directions explained. So if you look at this, it will become more clear. So north, northeast, east. And those are the 8 directions which it can go 7 squares in. Then the knight directions, so 8 directions. And then the under promotion directions and the kind of pieces they can go into. So 3 multiplied by 3 is 9. And then let's look at an example. So as the input, we get this board, which was like this complex input space. And then as the output, we get a plane. And this is the top plane of all the 73 output planes. And then each cell in one of those planes will get a probability that the algorithm wants to choose this move. For example, it wants to do this move by 15%, this move by 1%, and there are also actually some invalid moves. So what the neural network is not given is that there are invalid moves, but we are going to handle that a little bit later. So another example, it can move 2 squares forward. So these are all pawns, so they can move 2 squares in the beginning. Another example is, for example, for the horses, they can also move in the beginning to the northeast. So this is this movement and this movement. And then the night move can also like be to the other direction. And then we have had all the planes from the starting board actually. So if we want to do masking, and what masking means is that you remove the invalid moves. We can do like this. Okay, so then you only have the valid moves left. So those are all the pawns. The horse moves, the horses, the knights can only do the knight moves. Those are again pawns because they can move 2 squares forward, and then the horses in the other direction. And then what actually happens is that all the invalid moves that were selected by the network before, they get removed. And then you can calculate the probabilities again so that the sum of all probabilities is 1 again. Okay, so now we have had the input and the output. I hope everybody is still following. Are there any questions yet? Don't be ashamed if you don't understand, because I'm kind of going quickly. Nobody? Okay. So let's move on to the architecture then. We'll start with one convolutional layer, which I think most of you know. So it takes all of these planes, the input planes, and then it calculates new planes, and it actually calculates 256 new planes. So those are the kernels, and then a kernel size of 3 by 3, which is this. And then you have the amount of channels, which is 118, because there were 118 input planes. And then the padding same means that it stays the same size, so that you have an extra border around it. So that they stay 8 by 8 planes. And then you have the residual layers, which are a really important part of the AlphaZero implementation, because this makes sure that the training signal can go way back to the front of the neural network, because of course it is a very, very big neural network. And usually what happens when you train big networks, that there is a vanishing gradient, which means that the gradient, which is generated by the error at the end of the network, gets smaller and smaller, and the learning signal of the first layers is very small, and they learn very slowly. But by adding this skip connection, the back propagation can actually run not through these convolutional layers, but just directly to there, which means that the neural network, the earlier layers, will be able to train faster. Also batch normalization, which is also a famous technique used to not to have like the earlier layers train faster, and then so what this is the residual layer, and then you have these convolutional layers again, which were explained in the previous slide. So this is one of the 19 residual blocks in the network. So then we come to the value head, which tries to predict a number from -1 to 1 of what score the board currently has. These are some technical details. Let's skip through that. The policy head, which will predict a move to make. Also some technical details, softmax function at the end, of course. So then the Monte Carlo tree search. I hope you're still following, everybody. So this is an algorithm which is really nice, because previously always alpha beta pruning was used, but this is the first time, and this is why this algorithm is so unique. It's the first time that they used Monte Carlo tree search, and this kind of averages out all the scores that were given to a certain board. So for example, this is one board, and then the actions it can take, there are 3 actions it can take, so 3 moves. If you go to this direction, then you will get a prediction of how good this board will be. But by looking further in the tree and making an average of all the boards underneath, you will get a better approximation for this move, actually. So I will not fully explain the Monte Carlo tree search algorithm because it would take a long time, but that's the key of it. So you will get a better approximation of your policy, actually, so of the probability that you will do that move. And those are all the steps in it. And the most important ones is the selection, because this is a mathematical formula which is different in AlphaZero than like other algorithms usually. And then the playout formula, normally when you go into a certain board, then you roll it out till the end of the game. You check what the score of that game is. For example, I won at the end of the game. Then I get a reward signal of 1 to that node, and then I backpropagate it through my previous nodes. But now you just do a prediction with your neural network. You use the value head to see, okay, what's the score of this board, instead of looking all the way in the end of the game, and then you get your score, and then you backpropagate that. So you don't need to look at the end of the game, actually. So yeah, some maths, not going to fully explain it, but this is actually the mathematical formula which is behind the selection process. It's really interesting, and yeah, I also put some explanation with it, but you can read more in the paper itself. And so the play out. Okay, what's also really important is what Victor also explained already, is once you're doing reinforcement learning, you always want your agent to see their environment the same. So, for example, this is the agent that's playing with white, and it's playing against itself. So it will do a move with white, and then it will place itself into the, so then it's the black player, but then it places itself into the white player, which is actually the black player, so that it always performs as the white player, actually, but it's just a clever trick by mirroring the board. So by doing that, you don't need to have 2 separate agents, one for black and one for white. You just learn it by self-play. So then training the network, how is this done? So what you do is just keep on playing against yourself until you have done 700,000 moves with this Monte Carlo tree search algorithm. And then what happens is that for the policy head, you will get an improvement of your predictions, so from 0 to 1, because of the Monte Carlo tree search algorithm, because it averages it out, and it actually improves the predictions which you already made with your neural network. So you're doing like 800 simulations. If you take the average, it gets a better estimation of which actions to take, and that from those estimations, it can learn. And how do you improve the value network? You just play one game. The player who wins gets a +1 reward for all the moves it made, and the player who loses gets a -1 reward for all the moves it made before. And so the loss function takes into account the value head and the policy head. And this you have to repeat until you played 4 million games. So to do the math, you have 4 million games, about 50 moves a game. It's 200 million moves, and you do 800 Monte Carlo tree search repetitions. So that means 160 billion Monte Carlo tree search repetitions, actually. Oh, I missed the slide again. Okay, so what DeepMind is always like shoving forward is like this number. Wow, it trained in 9 hours really fast. And what they are also trying to do is, wait, I can't really see it. Okay, it's not in here, but normally they just say, okay, it trained with 64 GPUs or something. It's not that much compared to the number you see there. But what they actually mean by training is just the training and not the Monte Carlo tree search algorithm to like sample all your moves to learn upon. So they only take the training part, which is actually far less than the sampling you need to do. So in a dark corner of the paper somewhere, they then mentioned, oh, we used 5,000 TPUs to do the sampling. So that was kind of a surprise. So some insights and next steps. What is already said by my colleagues who stood here before is that you need to do incremental changes. So start by implementing the chess rules, look if everything is correct, then try to make a Monte Carlo tree search algorithm, already try to play the game, then only make a small network, try to let it learn a little bit, and then make it really big. So don't try everything at once, because then you won't know what's going wrong in the process. But since I only had 4 days, I skipped some steps. Also, an insight is that DeepMind has way too much computing power. But I think I might have an idea how I could potentially use some computing power for free, and that is Google Colab. I'm in the weekends. What I like to do sometimes, if I have some free time left, is read some papers or do some programming, and this is one of my ideas. So to learn the algorithm for free, I would use Google Colab, where you can get 1 GPU for 12 hours. And my idea is like but don't tell Google, I will create multiple collabs, then sample from each of those collabs, and send all my move samples to the cloud, just to save them in a storage bucket, and then do that in massive amounts and create a script for it. And then once 700,000 moves have been reached, then I take all the moves onto one collab and I try to train it. And once it's trained, I push my neural network to the cloud again. I pull it back on every collab, and then we sample again. So that's something I'm willing to work on in the weekends, and I really hope this will work. And if it does, it will make an amazing blog post. So I really hope it works. So are there any questions?
I would like to maybe ask Victor and Wart back to the stage again, because we didn't have questions for them. So you can ask Stan about everything you learned, or still have questions about AlphaZero. But also, if you have any questions about, let's say, Sim2Real, Unity, AlphaZero, shoot at all of them. So let's have like a question or 5 or so. I'll be walking around with
So for your implementation of AlphaZero, you did manage to train it from scratch for chess. So it does need all these Monte Carlo searches.
No. As you saw, this in the background is actually the implemented algorithm, and it's playing as black. But as you can see, black is playing kind of random moves, like it gives its queen away, it does nothing useful. So it works, but it hasn't been trained a lot.
Okay.
So that's why I'm trying to implement the collab thing I just said to make it better.
All right, I see, thanks.
Yeah.
Hi, my question is more related to the first presentation. You've trained your algorithm of on different environments, how does the algorithm learning goes on from one environment to the other? How?
So in general, I would say that it learns from one environment, and you cannot really you can extract the information from one environment to another. But this is the technique about, for example, called curriculum learning. You can really implement it, and there's a lot of there's examples available on ML agents how to do this exactly. But in theory, you have to see like the decisions the agent makes is its state space is its input, and its action is its output. Whatever you put in the environment doesn't really care that much. Your state space is what's defining the final action. So it all depends on how you read the state space from the environment. So it depends a little bit on the environment. But the state space, like what you give it from information, this is the crucial part.
Maybe to add a little bit on that, to give an example, we also use curriculum learning for the air hockey environment, and because it was taking way too long to just start scoring out of the blue, we basically train it first to touch the puck, but you don't have to train it that long, because if it over-focuses on touching the puck, it gets kind of rubbish at scoring. So you basically give it an idea of where it needs to go, stop it, and then train it in the other environment to try and score, and at that point you just change the rewards. So the actions, the state space, as he said, is very important, so it stays the same, or mostly the same, and then it's just the rewards that are different. So that's what we saw, and then over time you can, for example, we had a rule that once it got too good, the wall would come closer, until it was at the middle, like in the real game. So that's to give an idea.
So Wart, in your presentation, you talked about like two agents can share the same brain, right? So I'm a little bit still wondering about that. So you showed that you first are training against the wall, right, with the Pong game, and then eventually you want them to play against each other, right? So then they would be using the same brain, I assume?
Yeah. It's actually, then it will be almost exactly like the game that
right.
guys from ML6 were playing.
So what I can't wrap my head around is like, at that point, if they're using the same brain, can't they sort of try and cheat the game, like just I don't know, politely play to each other so that none of them scores because they're sort of governed by the same brain? Yeah.
So this is exactly like the reward function engineering that you have to do.
Right.
So you have to pay attention for these kinds of things. I can't really say out of the blue how you should exactly function your reward, but yeah, you just have to be cautious that you don't. You think it wouldn't do that because you're expecting it to behave in a certain way, but then it doesn't because it's just optimizing its reward. It's this, yeah. You have to pay attention. It can happen. I can only say it's possible.
So I guess it's quite a big change, right? Going from the one player against the wall to two players playing to each other.
Yeah. It's not an easy step, and that's why I said, like my last rule: don't do it if you don't have to do it, because then you have to keep into account that that one player it's left is the other player's right. And the ball, its velocity, positive x is then negative x, so you have to keep these things in mind. So that's why it becomes complicated. But
one comment on that.
We actually implemented the
Self-play, yes. And I looked it up, and it's important when you do it self-play that you really make sure that your state is independent of where you're playing. Because every brain has its own state, and that's the input. And it doesn't, if you set it up right, it doesn't matter where he is, because the input is the same. So like for us, we set up that way that we mirror our observations for our state. So basically, he's playing on the same side, but for us it isn't, but for him it is. And if you set it up that way, it's quite easy to do self-play, but it's tricky to implement the state that way. Like for us, it took a while because we had problems with our positioning and stuff like that. But if you set your state right, you can quite easily play against yourself.
Thanks.
I think I have 1 second left. Okay. Yeah.
Maybe a small follow-up question. How far can you get it into cheating it to thinking that it's the same thing? Like if you would play, because now you're playing a symmetrical game, but what if it's an asymmetrical game, but you know the asymmetry? So for example, one puck is smaller than the other one. Can you convert your state space with a known handicap so that it uses the same values to like, yeah, solve the game in a symmetrical way while it's still an asymmetrical game, because that's what you want to get, because otherwise you need two agents.
I think if I could answer this, I think what I would do is like you actually said yourself, is add it to the state space. You would just say what is the diameter of your puck at that moment. So it knows how wide it is at each moment next to, for example, its own position and the position of the opposite player. So at that point, it just gets extra information, and it kind of inherently trains two ways for both the small and the bigger paddle. Or even at that point, you could do it continuously. As you would say, you just give it any size, and it knows that size now. So it would just need to be trained from scratch again, but at that point, it would just work. Or that's at least what I would try.
I would also say that whenever you have this asymmetry, use two brains. There's probably a gray zone where there's an overlap, but try it yourself. I mean, this is already really complex, and then it's easy to get lost in stuff like this. It's really interesting question. I don't have an answer, but I guess it's easy to miss the overlap.
Not directly related to Unity, but more to reinforcement learning. What kind of interesting reinforcement learning projects did you work on in real life?
I cannot answer.
Same.
Well, yeah, it's non-disclosure agreements, but I think we can say that that there are yet to be very big business opportunities in reinforcement learning, at least that I know of. Like we do projects, yes, but like the real value on where it can be used in the real world is still at somewhat a hazy thing.
I will, if there are non-disclosure agreements, maybe what are your favorite real-world reinforcement learning solutions?
Actually, I do have an answer on that. I really loved the moment that Google did their data center cooling with reinforcement learning. So basically, they made a 3D version, like kind of in Unity, of their cooling system and of their data center, and then they just gave all possible actions to the agent of turning on the fans, like choosing the positions of the fan, and all of those things, like doing it over and over and over again. They managed, I think it was like 50 or 60% of an additional, of like efficiency gains in the cooling of their data centers, just because it had found some way of exploiting the heat, like how to maneuver the heat that they didn't think of. So you should Google it, because it's a really good blog post. I don't know too much about it, but it's a really cool real-life use case. And I think that's going to be the first use cases to show business value, like the optimization things, because that's what reinforcement learning is good at, I think.
If I may add, another one, my favorite, is from Microsoft and Siemens. Siemens has these big sawing machines, CNC sawing machines. And Bonsai is a reinforcement learning startup which got bought by Microsoft. They collaborate with Siemens for the calibration of these big industrial sawing machines. And it used to take a mechanical expert up to 40 hours to install and calibrate the machine. And it's like the same. You have like 20, 30 parameters to the machine. That's like the action space, right? You can turn this knob to calibrate the machine, and your reward function is then how accurate does the sawing get. It's very simplified. It's probably a lot more complex, but they succeeded to. When a technical human expert took about 40 hours to do the calibration process, and when it was completely controlled, steered by a reinforcement learning algorithm, they kind of reduced that down to 1 hour. So it's like a 40x reduction. So there are plenty. Another one is in wind energy management. I have a couple of very nice use cases out there. I did hear that the cooling center is not actually used by Google. I was a bit disappointed by that a couple of weeks ago, because I've been talking about that use case in many talks, and oh fuck, it's not true. No. So they didn't publish a paper on that. So I'm happy to see the AlphaFold paper now, because a lot of these stuff wait until you actually see the paper published by something like Nature, then it's peer reviewed. It's science, right? So look out for the papers, then start using it.
Yeah, and for me, it's actually anything. It sounds a bit fluffy, but anything that makes the world a better place. So, like AlphaFold is a really, really good example, I think, because it can solve problems which we currently have just using a computer, which is amazing. Because sometimes at ML6 we try to have these kind of projects as well, and then it's just really cool to sit behind your computer and like you're just imagining what you will be doing with that project, and that's the coolest part for me, if you can have a positive impact.
Okay, I think that's a nice way to round up with a positive. So you're welcome to play the games, both of them at the back of the office. Still hang around, have a beer, have a drink, and talk. Get to know a lot of people, right? It's a big crowd of interesting people, makes a network. Okay, thanks a lot.